The 1940 edition of the National Electrical Code allowed ranges and dries to be grounded through the neutral conductor, but it's important to note this was permitted, not mandatory. A separate equipment ground conductor was an option, also not mandatory. World War II had a significant impact on the electrical industry. This included shortages of materials such as copper, leading the NEC to make changes to conserve copper. One of these changes was the mandatory use of a separate equipment ground conductor for appliances and equipment. During the war, there was a moratorium on the production of certain appliances and home building. However, this wasn't the sole reason for changes in grounding requirements. The need to conserve copper also played a part. The fact that grounding through the neutral was permitted but not mandatory in the 1940 NEC suggests that World War II was not the only reason for the mandatory use of a separate ground conductor. Historical context and the need to conserve copper support this. It's reasonable to conclude that statements that World War II was not the only reason for this change are not entirely incorrect. World War II played a role in mandating the use of separate equipment ground conductor. However, it wasn't the exclusive reason. The need to conserve copper, along with the existing NEC provision allowing for grounding through the neutral, contributed to this decision. Therefore, considering the historical progression and the circumstances surrounding the 1940s, it's clear that multiple factors influenced the changes in grounding practices. To further clarify the evolution of grounding practices, it's helpful to examine the specific code sections and amendments related to grounding ranges and dries during this period. Firstly, the 1940 NEC, specifically Article 250, covered grounding requirements in general. The allowance for grounding through the neutral was typically found within the sections detailing appliance installations. Secondly, the exact language permitting neutral grounding needs to be examined. It usually stated that the neutral conductor could be used to ground the frames of electric ranges and clothes dryers, provided certain conditions were met, such as the neutral conductor being of sufficient size to carry the expected ground fault current. Thirdly, the amendments made during World War II needs to be understood. These changes likely involved adding specific language requiring a separate equipment grounding conductor for new installations, overriding or supplementing the existing allowance for neutral grounding. Fourthly, the rationale behind the code changes need to be looked at. Code-making panels consider the availability of materials, the safety implications of different grounding methods, and the practical feasibility of implementing new requirements. Fifthly, the impact of copper conservation is important. Copper was a critical war material, and reducing its use in electrical installations was a priority. This led to innovations in wiring methods and grounding techniques. Sixthly, understanding the role of underwriters' laboratories, also known as UL, is helpful. UL standards often influenced NEC requirements, and their testing and certification processes played a role in ensuring the safety of electrical equipment. Seventhly, compare and contrast the grounding requirements in the 1940 NEC with subsequent editions, such as the 1947 and 1953 editions. This helps to track the evolution of grounding practices and the factors that drove those changes. Eighthly, consider the practical implications of the code changes. Electrical contractors had to adapt to the new requirements, and homeowners needed to understand how to properly ground their appliances. Ninthly, analyze the debates and discussions among electrical engineers and code experts during this period. These debates often shed light on the rationale behind code changes and the potential challenges of implementation. Tenthly, look at any available documentation from code-making panels, or other organizations involved in the development and enforcement of electrical standards. This documentation can provide valuable insights into the decision-making process. Considering these points, the historical context becomes clearer. The 1940 NEC allowed neutral grounding as a permitted method, not a mandate. World War II and its associated copper shortages accelerated the transition toward mandatory separate equipment grounding conductors. However, the existing code provisions and the overall need to improve electrical safety also contributed to the change. This more nuanced perspective helps in understanding the complex interplay of factors that shaped electrical codes during this period. The evolution of electrical codes concerning grounding is complex, reflecting technological advancements, safety concerns, and material availability. To fully grasp the context of grounding practices around World War II, several key aspects of electrical systems and code development need to be considered. 1. The fundamental purpose of grounding is critical. Grounding ensures that electrical equipment and systems have a low impedance path to ground, allowing fault currents to flow safely back to the source. This helps to trip circuit breakers or blow fuses, quickly disconnecting the power and preventing electrical shock or fire hazards. 2. Understanding different grounding methods is important. The NEC recognizes several grounding methods, including equipment grounding, system grounding, and bonding. Equipment grounding connects non-current carrying metal parts of electrical equipment to ground, while system grounding connects the neutral point of an electrical system to ground. Bonding ensures that all metal parts are electrically connected to create a common ground potential. 3. The role of the neutral conductor must be discussed. In a typical electrical system, the neutral conductor carries the imbalanced current back to the source. In some cases, the neutral conductor is also used for grounding purposes, but this practice has limitations and potential safety concerns. 4. The historical progression of grounding requirements is necessary. Early electrical systems often relied on less sophisticated grounding methods. As technology advanced and safety concerns grew, the NEC gradually introduced more stringent grounding requirements. 5. The impact of technological advancements must be mentioned. The development of new electrical equipment and wiring methods has influenced grounding practices. For example, the introduction of 3-wire systems with a separate equipment grounding conductor has improved safety and reduced the risk of electrical shock. 6. The influence of safety standards should be noted. Organizations such as UL and the National Fire Protection Association, also known as NFPA, have played a key role in developing and promoting electrical safety standards. These standards are often incorporated into the NEC. 7. The economic considerations should be discussed. The cost of materials and labor can influence grounding practices. During World War II, the need to conserve copper led to changes in grounding requirements that reduced the amount of copper used in electrical installations. 8. The practical challenges of implementing grounding requirements is important. Electrical contractors need to be trained on proper grounding techniques, and homeowners need to understand the importance of grounding for electrical safety. 9. The ongoing evolution of grounding practices is important. The NEC is regularly updated to reflect new technologies, safety concerns, and best practices. Grounding requirements continue to evolve as electrical systems become more complex. 10. The legal and regulatory aspects of grounding are important. Grounding requirements are often enforced by local building codes and electrical inspectors. Failure to comply with these requirements can result in fines or other penalties. Looking at these aspects, a more comprehensive understanding of grounding practices and their evolution during the World War II era emerges. Grounding through the neutral was permitted but not always mandatory, and the wartime need to conserve copper accelerated the adoption of separate equipment grounding conductors. The interplay of these factors shaped the electrical codes and practices of the time. Consider the specific context of the 1940s and the materials available. Copper was indeed a critical resource during World War II, and its conservation was a national priority. This scarcity directly influenced electrical codes and practices. Also, recall the electrical systems that were common at the time. Homes often had fewer circuits and lower electrical loads compared to modern standards. Appliances like ranges and dryers were not as ubiquitous, and their electrical requirements were different. Remember the role of the NEC in setting safety standards. The NEC aims to provide practical safeguards for electrical systems, and its recommendations are based on the best available knowledge and experience. Now, let's consider the concept of grounding through the neutral conductor. This practice was permitted under certain conditions in the 1940 NEC, primarily for large appliances like ranges and dryers. The neutral conductor served as both the current carrying return path and the grounding path for the appliance's metal frame. Understand the advantages and disadvantages of this approach. One advantage was that it simplified wiring and reduced the amount of copper needed. One disadvantage was that it created a potential safety hazard if the neutral conductor became open or disconnected. If the neutral conductor failed, the appliance's metal frame could become energized, posing a risk of electric shock. Consider the alternative, which is the use of a separate equipment grounding conductor. This conductor provides a dedicated path for fault current to flow back to the source independent of the neutral conductor. The advantages of this approach are clear. Firstly, it enhances safety by providing a reliable grounding path, even if the neutral conductor fails. Secondly, it reduces the risk of voltage on the appliance's metal frame, minimizing the potential for electric shock. Thirdly, it improves the performance of circuit breakers and fuses, ensuring they trip quickly and effectively in the event of a fault. Considering the factors that led to the shift towards separate equipment grounding conductors, the wartime copper shortage was a significant driver. By requiring a separate grounding conductor, the NEC could reduce the size of the neutral conductor, thereby conserving copper. Safety concerns also played a role. As electrical systems became more complex and appliances became more prevalent, the limitations of grounding through the neutral conductor became more apparent. The NEC gradually moved toward requiring separate equipment grounding conductors for most applications. Considering the specific code changes that occurred during and after World War II, the 1947 NEC included revisions that further emphasized the importance of separate equipment grounding conductors. These revisions reflected the growing consensus that this approach provided a higher level of safety. Understand the long-term implications of these changes. The shift towards separate equipment grounding conductors has had a lasting impact on electrical safety. Modern electrical systems are designed with dedicated grounding paths, minimizing the risk of electric shock and fire hazards. Take a look at how grounding practices continue to evolve. The NEC is regularly updated to reflect new technologies and best practices. Grounding requirements are constantly refined to ensure the safety and reliability of electrical systems. The historical context of grounding practices during and after World War II is a reminder of the importance of adapting electrical codes to meet changing needs and priorities. The need to conserve resources, improve safety, and incorporate new technologies has shaped the evolution of grounding requirements. The introduction of ground fault circuit interrupters, also known as GFCIs, represented a significant advancement in electrical safety. GFCIs are designed to detect even small imbalances in current flow, quickly interrupting the circuit to prevent electric shock. They have become mandatory in many areas, such as bathrooms and kitchens, where the risk of electric shock is higher. Arc fault circuit interrupters, also known as ASIs, are another important safety device. ASIs detect arc faults, which are dangerous electrical discharges that can cause fires. They are now required in many bedrooms and other areas to protect against arc fault hazards. Solid-state devices and electronic equipment have introduced new challenges for grounding. These devices are often sensitive to voltage fluctuations and electrical noise, requiring special grounding techniques to ensure proper operation. Isolated grounding systems are sometimes used to minimize electrical noise and prevent interference with sensitive equipment. These systems provide a dedicated grounding path that is isolated from the regular equipment grounding system. Data centers and computer rooms often require sophisticated grounding systems to protect sensitive electronic equipment from damage and ensure reliable operation. These systems may include grounding grids, surge suppressors, and other specialized components. The NEC provides detailed requirements for grounding and bonding to ensure electrical safety. Article 250 of the NEC covers grounding and bonding requirements for electrical systems. These requirements are based on established safety principles and industry best practices. Regular inspections and maintenance are essential for ensuring the effectiveness of grounding systems. Electrical contractors should inspect grounding connections, test ground resistance, and verify the integrity of grounding conductors. Proper labeling of grounding conductors and equipment is important for safety and compliance. Grounding conductors should be clearly identified with green insulation or green tape. Grounding electrodes, such as ground rods and ground plates, should be installed in accordance with NEC requirements. The size and type of grounding electrode depend on the size of the electrical system and the soil conditions. Bonding of metal enclosures, raceways, and other metal parts is essential for creating a low impedance ground path. Bonding jumpers should be used to connect metal parts together, ensuring that they are all at the same ground potential. Grounding and bonding requirements for swimming pools, spas, and hot tubs are especially stringent due to the increased risk of electric shock in these environments. The NEC provides specific requirements for grounding metal parts, bonding conductive surfaces, and installing ground fault protection. Understanding the principles of electrochemistry can help in preventing corrosion of grounding electrodes and connections. Dissimilar metals can create galvanic corrosion, so it's important to use compatible materials and protect connections from moisture. Training and education are essential for electrical contractors and other professionals who work with grounding systems. They need to understand the principles of grounding, the requirements of the NEC, and the best practices for installing and maintaining grounding systems. Proper grounding is essential for electrical safety. By understanding the principles of grounding, following the requirements of the NEC, and implementing best practices, we can minimize the risk of electric shock, fire hazards, and equipment damage. The history of grounding practices is a reminder of the importance of continuous improvement and adaptation to new technologies and safety concerns.